In this video, we'll explore the contour diagrams of 3 example programs involving recursion, iteration, and first-class functions. So let's start with the program that computes the factorial by means of a recursive process. So the code is here, up in the notes. So define factorial of n. We have our base case. If n is less than 2, then we can just return 1. Otherwise, n factorial is equal to the factorial of n minus 1 times n. So 5 factorial is equal to 5 times 4 factorial, for example. Okay, and then in our program we say define the result as computing the factorial of 3. So 3 times 2 times 1 should give us 6, but the interesting thing here is what happens in the contour model when we walk through this recursive process. So starting on line 1, we say define factorial of n, so we create a binding between the name factorial and the lambda on line 1. So factorial lambda line 1 defined in the global scope, so we have our reference pointer pointing to global. All right, and all of factorial takes up lines 1 through 4, so the next line will be on line 5. Now on line 5 it says define result to be what happens when we call factorial 3, so we first have to call factorial 3 to find out. That creates a new scope for the bindings of the parameter n to the argument 3, and we get just that in the next drawing. So factorial single prime, where n has the value 3, and we've jumped ahead a little bit in this diagram to say that the first line we're going to be executing is on line 4. Technically you could say line 2 would be that snapshot, or we could say jump right to line 4 since that will be the active branch of our if statement. Either one is fine, but we need to have some sort of reference pointer to the body of factorial pointing us to the next line that will occur. Okay, so factorial of 3 creates a new scope. Inside that scope we have bindings for the parameter to the argument, and we're ready to execute the body of that function inside this new scope. So on line 4 it says times n factorial n minus 1. So times we don't find locally, we find the primitive, means multiplication. N we do find locally as the value 3, and for this we have to evaluate all of that. So factorial is defined in the scope above us, in the global scope, and n again is 3, so we're going to call factorial of 2. So if we do that, we get a new scope for factorial, where n is bound to 2. So we scroll down here, we get a new scope for factorial, our new contour. So factorial double prime, where n now has the value 2, and we're again executing line 4. Okay, so once we executed this call, we got a brand new second scope, a second instance of this factorial. Notice we're not finished computing the previous factorial. We still have to do the times n once we get the result out of factorial double prime, but ultimately we'll have that answer and we can collapse this to do the math. But before we can do that, we walk through this line, which again says times n of the factorial n minus 1. So times 2 factorial 1 in this case. The same thing happens there. We create a new scope for the new instance of factorial, where n is bound to this new value 1. So if we scroll down, we can see exactly that. We get factorial of 1, and we have a third contour in our diagram. Now, on this one, in this case, n is less than 2, so the active branch will be line 3, so we're going to just return 1 when we're done. So we have all 3 of these scopes essentially just representing a buildup of deferred operations. One contour per activation record representing those deferred operations up on the call stack. Right. So that's pretty much that entire example. So once we have that, this value here, this contour here returns 1, and that goes back to here where we have times 2, the result that came out of that. So times 2, 1 gives us 2. This returns 2, and now it says times 3, the result of this factorial. So we get times 3, 2, which gives us 6. That returns back to where the whole thing was called, which said define result as whatever comes out of factorial 3. A 6 came out of that, so we defined the result as 6. So we create a binding for that final result, and that's the entire thing. So the key here is if we have recursive functions, we have separate contours for each one of the instances of that function, because they all need to represent, or they all need to store their own instances of the parameter, for example. Okay, so that's the recursive version. Let's take a look at the iterative version as well. So the iterative factorial we've seen a few times. Let's bring that up. So here's the code for the iterative factorial. So we have our public function, which is factorial of n, but that's dependent on a helper function that has our running total and a counter to keep track of how far along in the process we are. So to start that, we'll start the product and counter as 1, and we'll multiply the current value of the counter into the product each time, and then increment the counter. So 1 times 1, and increment the counter. And then it'll be 2 times 1, and then increment the counter. Then it'll be 3 times 2, and then increment the counter. At that point, we'll have 6, and that'll be our final answer, because we're just calling for factorial 3. Okay, but let's see how this works on the contour models. So at line 1, we say define factorial of n, so we create a binding for factorial to the lambda on line 1 that was declared in the global scope. So we have factorial lambda 1 and our reference pointer. Now, most of the other lines of code here, 1 through 6, are inside factorial, so technically we could say the next line we're on is line 7, but since that's blank, I've jumped ahead and said the next line will be line 8. So at the beginning of line 8, and then we continue on. So on line 8 it says define result to be whatever happens when we call factorial of 3. So before we can figure out what the value is that we bind, we have to figure out what that value actually is. We have to do the function application. So factorial of 3 says create a new scope for this new instance of our function where the parameter n is bound to the argument 3. So we get factorial single prime where n is bound to 3. Now the body of factorial starts on line 2, so we have our line pointer. And when this whole thing is done, we're going to return back to line 8. So we have that as well. Okay, line 2 says define faciter with product and count as parameters. So the next thing that happens on line 2 is we create a binding inside factorial. Notice we're inside the body of factorial when we're making this define statement. And that define statement is for this faciter function. So we have the name faciter bound to the lambda declared on line 2. And then our parent pointer, this reference environment, is the factorial function because that's where it was created. What that means is inside faciter, when we want to refer to the variable n, we can do so because inside this, outside of this function is the scope for the factorial function. We'll get to that in just a second. So we define this function on line 2, and then most of these lines of code are inside that function, so the next thing is line 6. So on line 6 it says call faciter with the values 1 and 1 for the parameters prod and count. What that means is we create a new contour for faciter with a binding frame that has prod 1, count 1. Okay? But the question is, where do we put that scope in that contour in that frame? And the answer to that question is we follow this reference pointer. This reference pointer will always tell us which scope to create our new scope in. Okay, so since faciter was declared inside factorial, when it gets invoked, the contour for faciter gets created inside the factorial function. So faciter, we follow this pointer, and this is the scope that we create the new contour in. So inside this box. So we have faciter prime, and we have bindings for prod and count, the parameters to the arguments 1 and 1. The body of this function starts on line 3, so we have that. And this was called from factorial on line 6. So when we're done, we want to return back to line 6. And when line 6 is done, it should return back to line 8. Okay, so that's all of that. Now we're on to line 3. So on line 3, it says if count is greater than n, in this case it is not, because 1 is not greater than 3. So we have to look up all those variables, even the symbol here, which we find in the primitive environment, count we find locally, and n we go looking into the enclosing scope. So it's a good thing we created this contour inside the contour for factorial so that n would be in the enclosing scope. Okay, so that's what this pointer does. This says control where this new contour will be created to be inside of factorial. And what that means is that we can then access the variables of factorial from inside the body of faciter. So in this case, our if statement comes up false, so we jump down to line 5. So now for on line 5, it says evaluate this expression. Call faciter with new values for product and count. Specifically, we're going to multiply the current counter into our running product, and we're going to increment the counter by 1. Now, because this is an iterative process, or more specifically, because it's a tail call function call, so because faciter is the last thing that faciter does, this extra call here is the last thing that happens in that whole function, this whole expression, or this function call rather, can be tail call optimized, which means the activation record, or similarly the contour and binding frame for faciter single prime is no longer needed and can be replaced by all of the same for faciter double prime for the next instance of this function. So that's exactly what happens. We call faciter with these two new values. So count times prod is 1 times 1 is 1, and count plus 1 is 2. So we'll call factor with 1 and 2, and that will replace this contour with a new one. So click, and we get factor double prime. So essentially, if you want to break that down into 2 steps, it creates a second instance, a second contour for factor double prime, and then erases the original one, having mapped this return pointer from one to the next. So it takes the return pointer from factor single prime and sort of passes that on as well. So what happens next? So we're on, again, line 3 here. So we walk through all the same steps for factor double prime. Count still not greater than n. So we come down to line 5 and say, okay, calculate new values for count and prod. So multiply these two things together to get 2, and add 1 to count to get 3, and then call the function with these new values. So we get factor triple prime with 2 and 3. And again, we walk through it, and count still not greater than n, because n is also 3. So we go to line 5 again, and it says, call factor with, again, new values. 2 times 3 is 6, 3 plus 1 is 4, so we get factor quadruple prime, or I've started switching to Roman numerals for shorts. So in this case, it's very easy to just type out IV, and now we have the 4th instance of this function. Now, even though the previous 3 instances have all been destroyed, it's a good idea to keep track of which instance of the function you are on. That way you can verify that you've followed the correct number of steps. Okay, now if we get to factor with a count of 4, our if statement suddenly is true. So 4 is greater than n, which is 3. So that says go to line 4, which says return the value of product, our running total. So at that point, product gets returned from line 4 down to line 6. On line 6, this is also done, so it returns to line 8. And on line 8, we say, whatever came out of factorial 3, bind that to the result. So we return 6 from here to here, and then that gets bound in the result. Okay. So a couple things to point out here. If we have tail recursive functions, they do get tail call optimized, so those contours disappear when they make that tail call, when they call the next instance of the iteration. Now it's a bit odd that that happens in some cases and not others. I do want to point out that in factorial here, the call to factor is also a tail call as well. It's not tail recursive because it's not calling itself, but it is still a tail call. Now, not all tail calls can be optimized. In this case, it can't be optimized away because we still need the contour for factorial. Specifically, the reference pointer or the return pointer from, or sorry, the environment pointer for this contour, this thing here, points to factorial single prime. So when we're inside factor, it still needs that parent reference in order to have any context, specifically in this case, in order to have a value for n, for example. So we can't optimize away this outer contour, even though it is creating factor with a tail call. We can't get rid of factorial itself because it's still being referenced by that called inner function. Okay, so otherwise though, when factor calls factor 2 and factor 2 calls factor 3, for example, those can all be optimized away because there's no connection between those two things. The only thing really that we need to keep track of is this return pointer, and tail call optimization says take the return pointer from the first instance and just pass it to the second instance. So the second instance just keeps that same return pointer and goes back to where the first one was called from. Okay. I think that's it for that example. Good. On to one other example where we're dealing with some more tricky bits about these reference pointers. So these reference pointers, they're constructed, as I mentioned, when the function is defined or when it's declared. So when we have a defined statement or when we have a lambda statement, we construct that closure, that egg, if you follow the analogy from previous video, that contains a pointer to the function itself, the parameters in its body, and a pointer to the parent scope. Okay, but now those functions, or that closure itself, can be passed around the code as though it were just a first-class data, the same way we pass variables or numbers. So what happens to those pointers when we do that? So let's consider another example here. So here's an example code, another short one, 4 lines of code. So we define a variable, and we define a function, and then we call that function with a lambda. So it's a bit of a tricky example. Let's actually walk through the model itself rather than trying to understand the code on its own. So line 1 says define x to be 10. That's just creating a variable. So we have a binding in the global scope between the symbol x and the value 10. Okay, now we're on to line 2. Line 2 says do a similar thing, but this time with a function. So in this case, the function name is f, and the parameters are g and x. So we create a binding between the symbol f and the lambda on line 2. The define was on line 2. And this was declared in the global scope, so we have our pointer to the global scope here. Now the function spans lines 2 and 3, so we're now on line 4. Line 4 says define result to be whatever comes out of calling f with these two values. So this lambda will be g, and this 7 will be x. Okay? So if we evaluate this lambda, we get a procedure object. And that procedure object is declared on line 4 and is done inside the global scope. Remember, eval apply says evaluate the sub-expressions before applying. So before we can apply f, we have to figure out what is this lambda. It's not just the text, it becomes a closure right there. It says create a pair of pointers where one pointer essentially points to the text of the lambda. So we can see that there's a list of parameters and a list of expressions in the body. And that second pointer says point to the current parent scope, so the scope where this is currently happening. And since we're currently doing this inside the global scope, because we haven't yet called f, the parent pointer for this lambda will be the global scope. Now, the reason I have to belabor this before drawing it is that it doesn't actually show up in the model here. Because we're just saying, here's a lambda, remember lambdas are essentially unnamed functions, since we didn't give it a name, we're not binding it in any of the reference tables. So we don't have it inside the frame for the global scope as a name or anything, so we can't actually see that. But it is still creating something very similar. It'll be the lambda on line 4 with a pointer to the global scope, just without a name. Okay, and then all that information gets passed into f, and it all gets given names. So g gets the name of this closure that was passed in, and x is the name for 7. So let's walk through that. So the next step is we create a scope for f. So we have a contour for f. We have bindings for the two parameters, g and x. And the values for them, we have 7 for x, and we have the lambda created on line 4 declared in the global scope. So notice this pointer, for the first time, doesn't point to the current scope because it wasn't created in the current scope. It was created in the global scope. So that pointer is always going to reference the global scope. Okay, and that's the idea behind static or lexical scoping, as we've learned it, is that that scope, that parent scope, doesn't change even when the function moves around. So we pass this lambda into f. Now whenever we talk about g, we're talking about a function that was declared inside the global scope. So its parent pointer points to the global scope. So if it goes looking for free variables, it's going to find them in the global scope first. So let's see what that does. So if we have all of this, we're now on line 3, the body of f. And in the body of f, it says call g on the value 3. So we figure out what is g. So we go looking locally. We find g refers to the lambda on line 4 declared in the global scope. So if we want to create, if we want to apply g to a value, we create a new contour. And if we want to know where to create that contour, we follow this arrow and create it in this scope here. So because this was declared in the global scope, the contour for g is in the global scope. Even though the name is bound in f, the lambda itself was constructed in the global scope, so that's where the contour gets created. Okay, so not inside f, even though it was called inside f. It's created in global, so that's where it gets executed. Okay, so if we execute g, we can see g is this lambda. The lambda takes in a parameter y, so we gave the value 3 to that, so we have a binding y to 3. We have the name g prime, so in this case you could call it g because that's the name we referred to it here. It doesn't really have a name in the global scope, so it doesn't make sense to give it any other name, but it technically also went by lambda at one point. Oops, sorry about that. Okay, and then we have line 4 is the body of g because that's where the actual body of the lambda is described. Okay, so from there we can do the execution. So if we're in this scope and we execute the body of g, we say plus x and y. Well, we don't find a plus symbol locally, so we go into the enclosing scope, which is global, and the enclosing scope, which is primitive. Then we find it there, it means addition. Go figure. We find the y locally, right? Y is just 3, so that's easy. But what does this x refer to? We don't find it locally, so we go into the enclosing scope, and since we followed this parent pointer to create our contour in the global scope, then the enclosing scope is global, which means if we talk about x from g, it's a free variable found in the global scope. Okay, so very important, where we create this contour matches this pointer. Okay, because if we'd created it where it was called, for example, inside f, and we talked about x, then the free variable would refer to this x. But since it was created in the global scope, when we talk about x from here, we go to the enclosing scope, and here it is in the global scope. So we get plus xy, which is plus 310 to give us 13. That returns back to line 3, which returns back to this line 4 here to be bound to results. So the next step just says collapse everything, and result is bound to the value 13. All right. So a few things there. So the lambda was defined in global and then passed into the function as a first class value, but the reference pointer, that pointer to the parent scope or to the parent environment, doesn't change. It's static scoping rules. Okay. Also, technically, this call to G3 was a tail call, and G doesn't refer to F anywhere in it. Doesn't have any pointers. So technically, that could have disappeared. And we'll consider that in future examples. Since it was a tail call, we could have gobbled that up. But just to represent how this process works, and so we could keep this arrow on the screen mostly, I didn't actually tail call optimize this example, but technically this contour should have been, or sorry, could have been optimized away when G was running, right? We didn't need the X or anything in order to refer to it. Okay. In that case, if it was tail call optimized, this pointer would just point down to there, and the process essentially would work the same. It would do all the math. That 13 would return from here down to the end of line 4, define result. All right, so that's it for this video. We talked about recursion, iteration, and first-class functions with respect to these contour models. In the next video, we'll learn a little bit more about scoping and see different ways of organizing the scoping rules of a language. I'll see you in the next video.